Okay, so we're going to draw some analogies today with gravity. And you're going to have to remember back to about Unit 2 when we started doing forces. And we started acting vector forces. And it was difficult then, and it's going to be more difficult now. So you're going to have to resurrect that understanding and apply it again, because we're going to be doing some vector addition today. So let's think, though, a little bit about gravity. Remember, it's a field force. It's a force that's acting at a distance. It is always attractive. So if you have two masses, they're always going to be attracted to each other. How much they're attracted depends on the two things: what their relative masses are and what their radius is. So, and how big g is, right? Cavendish's constant, we call it. So we talk about two masses here. You guys are not feeling a huge attraction towards each other because your mass is relatively small. Now, if you start talking about planets and stars, huge masses, then the attractive forces become more significant, more measurable. Okay. We do talk about equal and opposite forces. So the force that the Earth might feel due to the moon, that pull on the Earth from the moon, is equal and opposite to the force on the moon from the Earth by Newton's third law. You might have thought that there'd be more of a force on the moon. Well, it's not that there's more of a force. It's the same force. It might tend to move more just because the moon is smaller. Okay, so back when we were talking about gravity, we talked about Cavendish's experiment. This is the experiment where he weighed the Earth. And what he did is he had this torsional balance, and he had this giant mass, these two rocks, and they would balance each other. And then he brought in close another mass. So he would bring in this great big mass, and then you have these two masses on a thing that would twist. And by bringing a mass close, it would feel this attraction, and the whole thing would twist a little bit. By measuring that torque, he was able to calculate what the value of g was. And once you calculated the value of g, he was able to calculate how much the Earth weighed, because it was g_mm over r squared. It was well understood what the acceleration of gravity was, but it wasn't understood what the mass of the Earth was. And you had to know g in order to get the mass of the Earth. So in electrostatics, we're going to do a very similar experiment. Okay, Charles Coulomb did this experiment with a torsional balance experiment using charge instead of mass. Okay, but it's the very same idea where you have, well, let's show it to you. Let's go next door. I'm going to pause the recording. Okay, so Coulomb, using the same principle that Cavendish did, set out to put charges on these little balls and then measure the torque that caused the twisting, and from the torque that caused the twisting, you could calculate the force between them, and then he would study what are the different forces depending on the different charges that were in the different balls, and he came up with a constant value. Okay, so this is Coulomb's law. Okay, it looks a lot like Newton's universal gravitation law, except instead of being g_mm over r squared, it's k q1 q2. Sometimes you'll see it written K, big Q, little q, just like big M, little m. Doesn't matter, right? It's two different charges, K, r squared. Okay? You could write this in vector form when you get into AP. You think about it that, but we're going to kind of keep it simple and just do it in non-vector form. But we are going to have to consider the vectors, but we're just not going to put it as part of the equation, essentially. So just like though we did with gravity, you have two charges, Q1, Q2, and you have equal and opposite forces between them. The forces are equal and opposite. It's a Newton's third law thing. Even if this is a huge charge and this is a little teeny charge, you're going to have equal and opposite forces because of Newton's third law. Now this shows an attractive force. In this case we have Q1 is positive and Q2 is negative, so there's an attractive force. But you could also have the scenario where they're both positive, in which case there would be a repulsive force. The force is going to tend to push them in the opposite direction. So that is one distinction between electric forces and gravity forces. Coulomb's constant K, and we'll talk about how different they are. So here we go. Coulomb constant K, he eventually was able to calculate experimentally to be 9.0 times 10 to the 9th. So it's a really nice even number. Okay, 9 times 10 to the ninth Newton meter squared per Coulomb squared. You're going to be using that a bunch in your calculations. 9 times 10 to the ninth. Just for comparison's sake, that's a really big number. You get that idea? For comparison's sake, the gravitational constant was about 10 to the minus 11th. So you see the order of magnitude of forces for gravity so much smaller than we're talking about the forces for electricity. Electricity is a very powerful force. Okay, but like gravity, the forces between charges varies as the inverse square of their separations. Like charges repel, opposites attract, charge is conserved, charge is quantized. That's everything you need to know about charge, all on one slide. If you had a pair of 1 Coulomb charges, 1 meter apart, the force of repulsion would be 9 billion newtons. So 1 Coulomb of charge is a lot of charge. Those are huge forces. Okay, now this is where it's going to get tricky. Okay, we're going to start talking about how to figure out what the forces are due to a charge scenario. Having several different charges, what are the forces that might be felt? The key is to think about vectors. Okay, so remember back when we did Unit 2, we said if you have a force going this way, you have a force going that way, you add them head to tail, and you can find the resultant force. And you can find it using the Pythagorean theorem, if these are at right angles to each other. So a squared plus b squared gives you c squared, and then to get the angle, you're going to use trig, opposite over adjacent or opposite over hypotenuse, whatever information you know. Okay, so we did that back in chapter 2. Now we're going to do it here, but it's more complicated because we have plus charges, we have minus charges, we have different distances. So I'm going to walk you through how to do a force calculation. The key, again, is to remember that these forces are vectors. That means you have to consider the magnitude, how big the force is, and you have to consider the direction. Okay, so all those things you have to consider. And I'll just tell you right now that 40% of you will miss this problem on the Chapter 8 exam. And it's only a 2-week chapter, right? So this is where people get tripped up. So take your time on your homework tonight. Give yourself plenty of space. Work out the math. Do it carefully. Keep track of signs. Be really careful in your work. Okay, so what we're going to do right now is we're going to try to figure out what are the forces acting here at this charge Q1. We have Q1 here, we have Q2 here, we have Q3 here. Okay? So if you have a little plus charge here, and you have a plus charge here, and you have a minus charge here, we say that the force on this charge is the superposition, or the addition of the forces due to these each individual charges. So I say, all right, well, what's the force here due to this guy? Okay, well, let's just think about it, right? This guy is negative. This guy is positive. So this is going to feel a force of attraction to this guy. So he's going to go this way. Okay? This is positive. This is positive. So it's going to feel a force of repulsion. It's going to want to get away from that guy. So it's going to feel a force down due to that guy. So the trick is, if I say, what are the forces at charge 1 at this location? You can say, all right, figure out what all the forces are due to this charge. Figure out what the force is due to that charge, and then add them together vectorially. You can't just add them together, just the magnitudes. You have to do it with vectors. So you can have a force going down. I say F12. F12 means the force on 1 from charge 2. Okay, F13, this is just nomenclature that helps you keep things straight because it can get pretty confusing. F13 is the force on 1 due to charge 3. Okay, so we're going to come up with magnitude and direction. So there's your force vector equation. The force on 1, the net force is the force on 1 from charge 2 plus the force on 1 from charge 3. And it's going to look like this. We know this vector is going to go down here. This vector is going to go this way because this was repulsive. So that's going to push that guy down. This is attractive, so that's going to push that guy over. So you go down, over, here's the resultant force. And you come up with the angle. And you can just, whatever angle you want to use to describe, as long as you're clear in your description or in your diagram, you'll be able to figure it out. All right, so let's take it through how we'd solve one of these. All right, so here's my hints. Find the magnitude of each force using Coulomb's law. Okay, so Coulomb's law, remember, is F equals K Q1 Q2 over R squared. Okay, so what I'm saying is calculate how big the force is. Right? If you have two like charges and they're really close together, then you're going to have a really big force. What is the force? K times her charge times my charge times the distance between us, divided by the distance between us squared. You know, and then there might be a smaller force over there due to Dory, right? And I'm positive she's negative, so I'm feeling a force that way, but I don't feel much of a force because it's much further radius. So the point is, figure out the magnitude of this force, KQ1, Q2 over R squared. Figure out the magnitude of that force, KQ1, Q3 over R squared. And then worry about signs. Okay, so get the magnitudes first using Coulomb's law. Then figure out the direction of each force. Right? So if it were me and Esther, we're same charge, I'm going to feel a force this way. So we got the magnitude, KQ1, Q2 over R squared, and then the forces drive us apart, so I know the direction is this way. And over here might be an attractive force, so I'm feeling something that way. Okay, so first get the magnitude of the force, and then you figure out the direction of the force, and then you add your vectors head to tail. To find the resultant, you want to use Pythagorean theorem, and then trig to find the angle. Okay, so this is all review. You've done this before, but you were kind of sketchy on it the first time, so hopefully after doing this, you get pretty good at this whole vector force addition thing. All right, so here we go. We're going to do a practice problem. So get a pencil and piece of paper so you can work this one out with me. Okay? Sometimes half the battle is drawing the diagram, understanding what you're given and drawing a sketch so that you can represent what you're told. Okay, so a 6 microcoulomb point charge is at the origin. A negative 3 microcoulomb charge is 0.2 meters to the right. Find the net electric force on a 1.0 microcoulomb point charge, which is positioned 0.2 meters to the right of the negative 3 microcoulomb charge. Okay, so I'm going to give you a minute or two right now. I want you to try to sketch out what that means. Draw little charges and label the charges. Are they plus? Are they minus? How much are they? Where are they? So go ahead and sketch that out. Okay, here's what I got. See if you got something similar. How are we doing? Okay, so what we're worried about is what's going on right here. Find the net electric force on this charge, which is positioned over here. So now what we have to do is figure out what is the force on this charge due to the minus 3 microcoulomb, and what is the force on the 1 microcoulomb due to the 6 microcoulomb. Okay, so my strategy said, first figure out the magnitudes of those forces. Okay, so I'm going to start with, and I call it F13. That means the force on the 1 microcoulomb that is due to the 3 microcoulomb. Okay, I don't care about sign right now. I just care about how big is the force. All right, so that force is KQ1 Q2 over R squared. So go ahead and write it out. K, 9 times 10 to the 9th. Q, 3 times 10 to the minus 6 coulombs, times 1 times 10 to the minus 6 coulombs. Again, we don't care about signs. Don't worry about signs when you're doing Coulomb's law. Go ahead and work that out. Divided by the radius squared. You think it's important to keep everything in SI units? Yes, yes. Did you notice that I changed microcoulomb into coulombs by putting a 10 to the minus 6 in there? I changed the radius is going to have to be in meters, not centimeters or decimeters or millimeters. Change it to meters. That way your forces are going to work out in newtons. Okay, so get everything in SI units and you should be good to go. So like a little sign, forget about your signs. You don't need to worry about your signs. Okay, so when I work it all out, hopefully you work it out too, and you'll get 0.68 newtons. Check it, see if you get that, and then we'll move on. All right, so let's move on. Now we want to do the force on the 1 microcoulomb due to the 6. So we set up the exact same equation, F equals KQQ over R squared. So the 1 to 6 is going to look like this. 9 times 10 to the 9th, Newton meter squared per Coulomb squared. That's Coulomb's constant. 6 times 10 to the minus 6 coulombs, that's the 6 microcoulomb charge, times 1 times 10 to the minus 6 coulomb. And then this distance between the 1 and the 6 is now 0.4 meters. So it's going to be the radial distance between the two charges you're worried about at that moment in time. So, hopefully you will agree with my calculation. So, the first strategy was to calculate the magnitudes of the forces, and that's what you've done. Next strategy is to figure out the directions of the forces. So now we're going to look at that force of 1 and 3. Okay, everybody get out your finger, right, your pointer finger, and point in the direction that one charge, the charge right here at the 1 microcoulomb, point in the direction that's going to feel a force due to the -3. Is it going to feel an attractive or a repulsive force? Which way is it going to go? Okay, good. Everyone's pointing to the left. Excellent. So that is going towards the left. It's going to feel a force in that direction. Okay, so I make a little vector. I make a little vector to the left, and the magnitude is going to be 0.68 newtons. Okay? Now, what about at the 1.0 microcoulomb right here, same spot, except what's the force direction going to be due to the 6 microcoulomb? Point your finger. What's the direction of the force? Good. It's to the right. It's to the right because it's a repulsive force. So I make a little vector. And it looks like this, 0.34 to the right. Now I add those two vectors together. The good news is they're one-dimensional vectors, right? So you're just going to get 0.68, subtract 0.34, and you get the net force is going to be 0.34 to the left. And that's how you would answer the question. You'd say the net force is 0.34 newtons to the left. Remember, when we're talking about vectors, you have to specify in your answer both the magnitude and the direction. Without the direction, the answer is only half right. And there's the correct answer, 0.34 newtons to the left. Okay, so that's it. Good. Okay, so we're going to have a couple concept check questions. These are going to make you think a little bit. First one. You can tell a ball is charged if it does which of the following when a positively charged rod is brought close to it. Okay? I want you to stop and think about this and maybe have a little conversation with your neighbors. I'm resuming the recording. For the record, every single person in the room got it wrong. So let's take you through why. Okay. So let's bring a positively charged object near a ball. One of the things we talked about yesterday is the fact that a metallically charged ball will become polarized. And so, if it's neutral, the ball is going to be attracted to the positively charged rod. So, can you tell if it's neutral or if it's negatively charged? You can't tell, because if it's negative, it's going to be attracted. If it's neutral, it's going to be attracted. So, in either of those cases, you're going to get the ball moving towards it. So, if it's attracted, it's not going to give you any information. But if it's repelled, then you know it must be positively charged. So the answer is B. Okay. Next one. Sphere A has twice the charge as sphere B. Which is the larger force? Okay, for the record, everybody got it right. It's C. Okay? Newton's third law, equal and opposite forces. So the answer is C, the same strength. Okay. Two metal spheres are on insulating stands, are initially uncharged and touching each other. A positively charged rod is brought near sphere A from the opposite of the sphere that is touching sphere B, and then sphere B is separated from sphere A. After separation, sphere A is A, uncharged, positively or negatively charged. Okay? Sketch a diagram, figure it out. Okay, so here you go. You got the two spheres together. We're going to call them A and B. You bring a positively charged nearby. So what's going to happen is this polarization. The minuses go to the left. The pluses go to the right. Pluses want to get away from that positively charged rod. Then you separate the rods, and the positives stay on the B, and the negatives stay on the A. So the answer is C, negatively charged. Okay. Which of the following is false regarding electric charge? Okay, so we all agree that the answer is C. All right. And here we go. To decrease the electric force between 2 point charges by a factor of 9, the distance between the charges should be... Okay, good. The answer is A, increase by 3 times. You increase the distance, that's going to decrease the magnitude. All right, here we go. An initially uncharged metal sphere is on an insulating stand. A negatively charged rod is brought near the sphere, and then the sphere is grounded. When the ground wire is removed from the sphere is what? Okay, we agree the answer is B. Because if you bring a negatively charged rod by, they're going to polarize. And then if you ground one side, then the negatives run away, and you're left with a positively charged party. And so you have a net positively charged. Good. Okay. And this is a really good question. So you're going to have to sketch this one out and work it through. All right? So 5 nanocoulomb charges at the origin, -5, 20 centimeters to the right. A positive test charge is midway between them. Find the direction of the force on the test charge. Okay, a test charge is like a little charge that doesn't have any mass. It's like, okay, if I put something plus here, where is it going to feel a force? Is it going to be to the left? Is it going to be to the right? So imagine a little positive charge. Which way is it going to feel the force? Okay, so that's the question. Okay, so we have mass disagreement about the right answer here. So let's think about what's going on. If you have 5 plus 5 nanocoulomb and minus 5 nanocoulomb and 20 centimeters between them, and you put a little plus charge in between, okay? So now what you want to think about is, what is the force on that little plus charge due to the minus 5 nanocoulomb, okay? If you were standing right here and you were positively charged, which direction are you going to feel the force due to this guy, the red one? To the right or left? To the right. You're attractive. You're like, woo, let's get together, right? And then let's talk about, so that one is going to be to the right. We all agree on that, right? Now, what about the plus charge due to the positive charge here? Is there a force? What is the force on this guy due to the blue charge? Is it going to be to the left or to the right or up or down? To the right. Yeah, to the right. So both of these charges, the plus and the minus, are going to tend to pull this little test charge to the right. So the answer is to the right. If they were both positively charged, then you guys would have been right. It would be stuck in the middle, right? Because they'd be feeling a force to the right, a force to the left. They'd be equal and opposite. They're not equal and opposite because the two charges are different in sign.
Can you have a negative test charge?
Yeah. Yeah. So if it was a negative test charge, what would be different? The force would be to the left, right? Okay, good. So you have two net forces. The net overall vector is going to be to the right. Okay, and that's it. That's all I have for today. So take a look at, I know you're tempted to just pack up. You got 2 minutes, so take a look at the homework and maybe you start sketching out the first problem or two.